Hi, my name is Pushpita Chanda. I am a PhD student at IIT Delhi under joint PhD program of University of Queensland and IIT Delhi. I am a PMR fellow. So today I'll discuss week 1 assignment of this course, Mathematical Methods in Physics 1. If anyone has any question, raise your hand and ask. I'll try to solve in this session, or I'll get back to you in the next session. And please comment if I am going too slow or too fast. Okay, so I'll start now. So first question of the assignment is, using vectors, check which of the following statements is true. Here are 4 statements. From basic understanding of mathematics, we can guess which of them are true and which are false. So we know that each of them are true, but we need for this course we need to know how to prove them via using vector. So let me prove those things. First, there is some issue with my writing device today, so I am presenting via another account. Sorry for that. So the first statement is, the diagonal of the parallelogram bisects each other. We know it is true. So let me prove that via using vectors. So this is a parallelogram ABCD. The diagonals are AC and BD, which intersects at point P. So let us assume the side AB is a vector A and AD is a vector B. AB and DC are parallel, so DC is also a vector A and BC is also vector B, as AD and BC is parallel. So from vector we can assume a vector AP here, and this is the direction of BP. Similarly, the direction of PD will be in this direction and PC will be that. So from the picture, let me use another. In this triangle A, B, D, D, AB is A and BD is BD, which is, I have not given any name there, and AD is B. So from this triangle we can say that BD plus A, that this direction is BD, or A plus BD is equal to B. You can say that. So BD will be B minus A. And similarly we can say AC, which will be this vector, or I can use green. AC will be AD plus DC. AD is vector B, and DC is A. So BD is B minus A and AC is B plus A. But we have to prove that AP is the midpoint. P is the midpoint of AC and as well as BD. So the P is the midpoint of BD, or we can say that P situated on the line BD. So the direction of AP will be as direction of AP will be along AC, or direction of BP will be along BD. So we can write AP, which direction will be along AC, some constant A plus B. This is scalar. And also BP will be in the direction of BD. The direction is B minus A. Sorry for this mistake, it is scalar. So AP will be in the same direction of AC, that's why we can write this way, and BP will be the same direction of BD, so some constant and the same vector. Now AB is AD plus DB is AP plus PB. PB we can write minus BP. Here AP we know Y into A plus B, and BP is X into B minus A. AB is A. After simplifying that, we know Y minus Y plus X into A minus plus Y minus X B. The line we can write this way, X plus Y minus 1A, because here is also a 1A, plus Y minus X B is equal to 0. A and B vectors are non-collinear. So from the above equation, A and B will be non-collinear when X plus Y minus 1 is equal to 0 and Y minus X is equal to 0. So from that condition we get X plus Y is equal to 1, and from this condition we get Y is equal to X. So we can say that X is equal to Y is equal to half. So if X plus is equal to Y is equal to half, so here we can write AP is equal to half of A plus B, and similarly BP is half of B minus A. A plus B is AC, so AP is half of AC. Okay, when I'm explaining, it is not visible. Where?
Clearly দেখা যাচ্ছে।
Okay, okay, clearly দেখা যাচ্ছে না।
দেখা যাচ্ছে।
ও দেখা যাচ্ছে।
জুম করতে বলুন ওনাকে।
Okay, okay. I'm a Bengali. I understand Bengali, but as it is a national level course, even I have to speak in English so that everyone can understand. So she is saying that it is visible. Bhuvaneshwari, please zoom in, because in my screen also it is visible. Or you can minimize my face with screen showing my face, then you can see the board. Is it now okay, Bhuvaneshwari? Can you see now, or is it visible? Miss Bhuvaneshwari? Yeah, please check. I am taking first time any course, so please say if it is impossible to understand, or I have to explain more or less. Or you can pin this presentation. Okay, now you can see. So I will continue now. So from this, when we put y is equal to x is equal to half, we can see that AP is half of A plus B. A plus B is half of, not A plus B is half of AC. Half of A plus B is equal to half of AC. And similarly, half of B minus A, we can say half of BD. So from this point we can say that P is midpoint of AC also and BD also. So P is midpoint of both the diagonal. So we can say that A is true, which is all we know, that A has to be true. Okay, now we'll prove the statement B. The statement is the line segment joining the midpoints of two sides of any triangle is parallel to the third side and half its length. So we know it is true from our class 10 knowledge, mathematics knowledge, but here we have to prove it via vector notation. So here I have drawn a triangle ABC. So A, B, C. Let's draw like that, and CB is equal to A, CA equal to B. And this point is M, this point is N, CM is up to this point and CN is up to that point. So the statement already said that midpoints of two sides, so CM, or we can say that M is midpoint of CB, so CM would be half of CB, which is half of A. Similarly, we can say CN is half of CA, which will be half of B. From this value, CB, if CB is A and CA is B, and from triangle rule we can see that CA plus AB is equal to CB. CA is B, AB is AB. I have not given any specific name to that side. CB is A, so AB is A minus B. So if I want to know the vector of NM, so I will consider this triangle CNM. So from this triangle we can see that CN plus NM is equal to CM. We are interested on NM, so NM is equal to CM minus CN. CM is half of A, we have already produced that, and CN is half of B, so half can be taken out, the common, A minus B, and we have already extract that AB is equal to A minus B, so half of AB. This means the magnitude of NM is half of AB, and also they are in the same direction. So we can say that NM and AB has same direction or they are parallel. And NM has the magnitude of AB. So statement B is also true. Now we came to statement C. So statement 1 is true, B is true. Statement C is, in a parallelogram, the two lines from one corner of the midpoints of the two opposite sides trisect the diagonal they cross. The two lines from one corner of the midpoints of the two opposite sides trisect the diagonal they cross. So there will be some mistake. CD. So D is the midpoint of OA. Like the previous parallelogram, if we name it as A. CB is if A, then O is also A, and OC is if B, then AB is also B. So in the triangle OAB, OA plus AB is equal to OB. So we have given name OA A, so A plus AB, AB is B, sorry, is equal to OB. And we have also know that AB is also OC. So AB can be written OB minus, okay, someone is there, OB A is equal to OB. Good. So OB is equal to A plus B. D is midpoint of OA. So OD up to this point is half of A. So position vector of the point, this point, which divides CD in the ratio 2:1, it's 2 into A by 2 plus 1V 2 plus 1. It will become A plus B by 3. And this point 1:2. Any point which divides the ratio OB in the ratio 1:2 is 1, A plus B, 2 into O. The position vector of O is 0. The position vector of B is A plus B. Same, the midpoint of the point which divides CD in 2:1, here the position vector of C is B and the position vector of D is A by 2. So this is that point's position vector which divides the CD in 2:1, and this is the position vector of that point which divides OB in 1:2. The end product, or you can say output, is same. So we can say that both are the same point. So CD trisects OB. So C is also true. Now it's time for D. Let me check if there is recording or not. Yeah. So fourth statement is the sum of the squares of diagonals of a parallelogram is equal to twice the sum of the squares of two adjacent sides of the parallelogram. This statement is also true, and we are gonna show that using vectors. So here O is the midpoint. AC and also BD. Okay, so first we will consider the triangle ABD. In also O is the midpoint of BD, so BO is equal to OD is equal to half of BD. There is a theorem called Apollonius theorem, which is kind of a Pythagoras theorem. Using that, we can write that AB square, AD square, square means the dot product of AB, so this means AB dot AB. Similarly, this means AD dot AD is equal to 2AO square plus 2BO square. You can name it 1. Then from triangle CBD, we can write again BO is equal to OD. CBD is that triangle. Again, is equal to half of BD. Again, using that Apollonius theorem, it is CB square plus CD square is equal to 2CO square plus 2BO square. And now if we add 1 and 2, we get AB square plus AD square plus CB square CD square is equal to 2 into AO square plus BO square plus CO square plus BO square. So there is 2BO and AO is equal to CO. So you can write 4 into AO square plus BO square, which can be written like this. Two into AO is AC. 2 into AO is AC because O is the middle point of AC. Similarly, 2 into BO is BD because O is the middle point of BD. So D is also true. I have shown all this calculation to make you understand, but for MCQ purpose, you can tick all of them because you know the statements are true from your higher secondary mathematics like knowledge. Now we have come to question number 2. So the question is, consider the ordinary vectors in 3 dimension. 3-dimension vector will have 3 direction x, y and z. Here Ex, Ey, Ez are unit vector along direction x, y and z with complex components. The Ax, Ay and Az we can assume that is complex. So which of this following statement is true? The first condition is the subset of all vectors with Az is equal to 0 constitute a vector space. A vector space has to satisfy 4 conditions. The closure condition, in closure condition there is 2 conditions, like if A belongs to a vector space V and B belongs to a vector space V, then A plus B also needs to belongs to vector space V. And if alpha is a scaling component or a scalar product, you can say, which will increase the magnitude of A, not definitely will not change the direction of A if it is not a negative scalar. It also has to belong to V. There need to be an identity for identity element and an inverse element. Sorry, not identity, null. If we add those things with A or B, it will unchanged A and B, and there need to exist a inverse thing. For A it will be minus A, which will give us the null. So the minus A need to be a minus A also need to belongs to V. So we have to prove all these things one by one for each statement and see if which one of them are true. So we can test both of the closure. Okay, what happened? We can test both of the closure property at the same time. Suppose A is a vector, components I have given the name AX, AY, AZ, and B is a vector, components are BX, BY and BZ. As we have been told that AZ is equal to 0. AZ is equal to 0 means here they want to say that the coefficient of Z direction is 0. It doesn't mean only AZ 0, it also means BZ is also 0. Okay, so it will become 0. Now generally we have to do what? Prove that A plus B belongs to the vector space V. Let us assume A belongs to vector space V1, B also belongs to vector space V1, and alpha A belongs to vector space V1. But we can prove these two closure property at once. Like this, we assume a vector C which is alpha A plus beta B. Here alpha and beta belongs to a vector space R. Okay. So what will be the C? Alpha into AX, EX plus AY, EY plus AZ, which is 0, beta into BX, EX plus BY, EY plus 0 into EZ. After simplification, we will get alpha AX plus beta BX into EX plus alpha AY plus beta BY into EY. These are the unit vector along X, Y and Z direction, and also 0 EZ. So if we look at A and B, the structure of this vector when we write in this way is there is a coefficient or with EX, a coefficient with AY, EY and a 0 coefficient with EZ, and same for B also, you can see. So for C we get the same. We can name this coefficient as Cx, because Ax is also a coefficient, Bx is also a coefficient, alpha and beta is real number. So it is, we can say it will be some coefficient. So it will be in the construction of Cx, Ex, Cy, Ey and 0 Ez. So C also belongs to vector space V. Now we need to prove that the identity vector for all these A, B and C, any vectors which belong to this vector space also belongs to their specific vector space also. So 0 is Ex, we can write in this way, Ey, Ez. See, we have been given that Az, which is the coefficient of Ez, needs to be 0. So here the coefficient of Ez is 0. So 0 also belongs to this vector space. There needs to inverse vector, existence of inverse vector. So for A, inverse vector will be A minus A. For minus A, its direction will be the reverse of A. So A is that. So minus A will be minus Ax Ex minus Ay Ey plus minus 0 Ez. Minus 0 is still a 0. So minus A also belongs to V1. So this 4 condition has satisfied. So we can say the statement A is true. We'll see that if statement B is true or not. Statement B is all vectors with Az is equal to 1 calculation. Now we have to see if we put 1 here, what will happen. At first, by seeing that, you can assume that if Az is equal to 0 satisfying makes this a vector space, why not Az is equal to 1? So you need to make those calculation before ticking any option. So let me do this calculation. Put this 1 here. Okay. So here there will be a 1. So what will be happen here? Here we'll get alpha plus beta Ez. Alpha plus beta. Here we get the coefficient of Z component is not 1. It is alpha plus beta. So alpha plus beta make the constitute 1. We'll put constraint on alpha plus beta. For not for all value of alpha plus beta it will become 1. So to satisfy vector space condition, first two condition, the closure property is not being satisfied by this condition. So B will be false. A is true, B will false. The next condition is okay. And for also we can if you want to check the third condition, identity vector, here the coefficient of Ez has to be 0, but we need 1. Those 0 will not be belong to that vector space V2. Let us say that vector space is V2. Similarly, we can prove that C, what is this? The subset of all vectors with equal components constitute a vector space. So A will be here ax ex plus ay ey plus az ez. Ax is equal to ay is equal to az. A belongs to a vector space V3, say, because it's third condition, so I have given the name vector space V3. Similarly, B is bx ex, so it will be ax ex plus ey plus ez, because ax is equal to ay is equal to ez, so it will be by ey bz. So bx by is equal to bz. Remember, the statement, the subset of all vectors with equal components. Equal components means the components or coefficient of ex, ey, ez of each vector is same, not with the other vectors coefficient of the same vector space. So ax is not equal to bx. Remember that. So again, C is equal to alpha A plus beta B will give us alpha into ax ex plus ey plus ez plus beta bx ex plus ey plus ez. Okay, so the x coefficient of C will be so we can see that both the coefficients are equal. So closure property satisfies. Then identity. Zero will be the identity because a plus 0 will give a. For 0 we have already know. This way we can write 0 vector. All the components are equal. For inverse component, if we consider minus a, because a plus minus a give us identity 0, minus a, it will be ax, sorry here I have made a mistake, it's not ax, it's ex. It will be the inverse of a. Minus a also belong to V3. This 0 vector also belong to V3. So the statement C is true. The subset of all vectors with a z is equal to 2ay is equal to 4ax constitutes a vector space. It will also be a true. Let us check. Now suppose A belongs to a vector space V4 now this time. Anyway, you can give the vector space name as you want, but generally it is V1, V2, V3, V4, or if you want to prove one thing, so it is only V. Ex plus ay ey plus az ez. So what does it mean? Az is equal to 2ay is equal to 4ax. So if we want to write all those things in terms of ax or az, or you can also write in terms of ay, but the main point is you have to write all those things in terms of either ax or ay or az, not at the time with all three variable, because you have given a condition. So ax, okay, so ey, so ax, keep ax same. We are given 2ay is equal to 4ax, so ay is equal to 2ax, so we can write 2ax ey. Similarly 4ax ez can be written as ax common, ex plus 2ey plus 4ez. Similarly for b, you can write in the same way. Always remember, here conditions are given as a component of A, but it's not like in general A. The components condition is given for any vector space's components condition. For B, it will be bz is equal to b2 2by is equal to 4bz. Okay, so C will be alpha A plus beta B, so alpha into ax plus ex plus 2 into ey plus 4 into ez, beta bx to ex plus 2 into ey plus 4 into ez. After grouping the coefficient of ex at the same pole, alpha ax to beta bx ex plus 2 into alpha ax plus beta bx is equal to, and plus 4 into alpha ax plus beta bx ez. So if we give this name Cx, Ex, so it will be 2 into Cx Ey and it will be 4 into Cx Ez. It is the structure of A, also the structure of B. So C vector belongs to the vector suppose V4. It satisfies the first condition, closure property, to make a vector space. Then we need to see the identity 0 to Ex plus 0 Ey plus 0 Ez. We can write it like that. Like 2 into 0 Ey into 4 into 0 Ez. So 0 also belongs to vector space V4. And the inverse. Let's take the inverse of A. So it will be the minus Ax Ex minus Ay Ey plus minus Az Ez minus Ax Ex minus 2Ax Ey minus 4Ax Ez. So it is Ax 1 plus 2ex plus 2ey plus 4ez. So minus a also belongs to V4. So here A, C and D is true. Okay, only B is false. Yeah, we can skip the similar examples. You say which question you want me to explain. If anyone don't have any problem, or like in same question I can explain the first statement if it is true or false, or how we can like explain that, then I can skip whatever you say, because I need some time to write, so that time need to be spared, but we can skip some things. Yeah. Similarly, question 3 is also like constitute a vector space. If anyone don't have a problem, then I can skip that, and if anyone has a problem, I can explain it later. I have problems in row reduction of matrix, ma'am. Row reduction. Okay. So let me skip the question 4 also, if any of you don't have a problem. Actually I can't skip the problem because I need to like post this recording in the channel also. All the problems have to be there. So which is the row reduction problem, I will solve it first, then I will solve other ones.
Ma'am, please explain these questions and all
of the question. Okay.
Ma'am, these questions, all of the options.
I can understand you.
ম্যাম আপনি এই কোশ্চেনের সমস্ত অপশনগুলো একবার বলে দিন, আমি ঠিক বুঝতে পারছি।
Which question? Question 3?
Yes, ma'am.
Okay. Okay. So let Devi, I will explain the row reduction of matrix problem. Let me explain the question 3 first. So, which of the following collection of polynomials constitute a vector space? Okay. The collection of all polynomials of degree less than n in x. So, let's consider a vector space V1, which will be the function of x. Fx, function of x or fx. So the form of polynomials of a degree less than n minus x will be a0 x to the power 0 plus a1 x to the power 1 and so on. So a n minus 1 x to the power n minus 1. All ai constitute space C, and I needs to be 1. See, when you are solving MCQ question, you don't need to write all this thing, you need to understand. But when you are like are given 5 or 6 number to explain all those things, so you need to write the notation correctly. So function v1 fx. So to prove the closure property, we need two function fx gx, each have form of this, fx also and gx also. So this thing fx, which I have written a0 x to the power 0 is 1, a1 x to the power 1, a2 x square, and so on, an minus 1 x to the power n minus 1, where ai means a0, a1, a2, a3 all constitute a vector space also, which is called C, which is a complex number in general. I is equal to 1 to n minus 1. It can be written like this: I is equal to 0, n minus 1, aix I, and gx also can be written like this: I is equal to 0, n minus 1, bixi. Here you can also write j. These are I, j, all are dummy indices. Like, it doesn't matter you call it I, j, l, m, p, q, whatever else. All I like start from 0 and end at n minus 1. So first, closure property. So we assume a function hx, which will be alpha fx, similar to the previous one, where there will alpha a plus beta b, here alpha fx plus beta gx. Okay, so we can write this: I ai xi plus beta bixi. For simplicity, please don't write here y. You don't need that. Even you write here y, x and y are like same here, because the polynomials here in the question, they have not mentioned it is a x, polynomial of x or polynomial of y. If you assume it is a polynomial of y, there you can introduce another summation, and there will be another x and y will be dummy. But for simplicity, don't do that. So here we can write this is a alpha ai plus beta bixi. This can be written as C. So hx also follow the form of fx or gx, so it is also form of the same vector space. Then identity. Identity, any polynomial will be 0 of x. 0 of x is 0 when f of x or g of x or h of x can be added with 0 of x or 0, it will give back fx, gx or hx. So 0 of x will be 0. ai, we can write it in the form of ai xi. I is equal to something 0 to n minus 1. ai, all ai is 0. If we put all ai is equal to 0, then it will give us 0. So 0 function is also a vector, also a component of a vector space V. And inverse, if fx ai xi I is equal to 0 n minus 1. So its inverse will be ai xi I is equal to 0 n minus 1. Devi, I'll explain that row reduction matrix problem to you. Like 3 was nearer to 2, so I was explaining that fast. Otherwise, I will explain all the problem. I am a little slow, but I will cover them in next session, or I will make some PPT so that you can like we can move a little faster. So this f of minus f of x also belong to the vector space V, or you can write like f dash x also. So fx plus f dash x will make you 0. So option A is true. Similarly, for option B, the collection of even polynomials with complex coefficient of degree less than 1 then n in x. So like please understand clearly, even polynomials only had even components like a0, a2 and all that. There will be no a1. When a and fx and gx don't have a1, then automatically hx will not have a1, and they will constitute a vector space again. Similarly, ox, 0x, you can write 0x any way you want. So only even components are there. And when fx doesn't have odd components, how can its inverse will have odd components? So they will form a vector space. I am now writing this again, but Payal, is it clear to you?
Yes, ma'am.
Yeah. Option C. Option C is what? The collection of all polynomials of degree less than n in x which take the value 1 at x is equal to 0. At x is equal to 0, they all take value 1. Like at f0, they are 1. So closure property. See, these things you have to write when you will give like they are all common. Okay. So I am not writing this. Okay. So v2, let's say fx constitute v1 and also f of 0 is equal to 1. Okay. So fx gx alpha beta. Okay, alpha plus beta g of x is equal to hx. Right, it will satisfy. Okay, alpha of fx plus beta of gx. If fx got f0 is equal to 1, similarly g0 is equal to 1, so when let us assume h0 will be alpha into f of 0 plus beta into g of 0, it is alpha into 1 plus beta into 1. But alpha plus beta is not equal to 1. If h needs to be in the vector space v2, then h0 is need to be 1, but alpha plus beta is not 1. Okay, so first closure property, it will not satisfy. When some vector space is not satisfying closure property, you don't need to prove another identity and all other things. It doesn't satisfy. You need to just stop there. Then D, which is D, the collection of all polynomials of degree less than 1 in x which take the value 0 at x is equal to 1. Okay, at x is equal to 1, f1 is equal to 0. Similarly, g1 is equal to 0. We have to prove h1 is equal to 0 to prove closure property, right? Because for rest other value of x, everything is same as option 1. Okay, so h, which is that alpha fx plus beta gx, we need only h is equal to 1. I am writing direct f is equal to 1 because alpha doesn't care what is inside f. Okay, so alpha is a constant. At f is equal to 1, not f equal to 1, function of value at x is equal to 1, it is 0. Similarly, it is also 0. It will give you 0. So h1 is giving you 0. So it is satisfying the closure property. Okay, here it is not. See, when you see the is not satisfying, then B is also satisfying. But there is a difference between those two. There, it at x is equal to 0, f of 0 is equal to 1, but h of 0 doesn't come 1. So that is 1, because then also there is identity. So 0 vector identity and inverse will also satisfy for f1 0, like inverse will be minus of f1, so that will be also 0. And also if you add a 0 null, for that also it is in the vector space. So option D is correct. Now first, like try problem number 5, because it is a row reduction. I will explain problem number 4 also, but first take this problem number 5. So the system is x plus y plus 2z is equal to 1, x minus y plus z is equal to 2, 2x plus 4y plus 5z is equal to 1. Okay, we can write this equation as mx is equal to c, right? So m can be written as 1, 1, 2, because here coefficient is 1, here also 1, this is 2. Similarly, the next line will be 1 minus 1 into 1 into, sorry, not into 1, it will be 2, 4, 5. X will be x, y, z, and c will be 1, 2, 1. The augmented matrix will be this. This is written as 1, 1, 2, 1 minus 1, 1, 2, 4, 5. Here we can write, we write this way. Okay, now we need row reduction. Okay, for row reduction, what we have to do, we have to make this point 0 and keep one row intact. Usually we keep the first row R1 intact. Okay, you can keep any row, R2, R3 intact, whichever is feasible to you. Okay, so here it is 1, it is 1. How will it become 0? If we minus 1 from 1. Okay, we will not care about this minus 1, 1 and 2. We are only making this 1 to 0. Okay, so what we will do, R2, new R2 will be R2 minus R1, so that it becomes 0. Similarly, we want to make this also 0. 2, we need to make 2 also 0. So how can it will 0? 2 minus 2 will be 0. How can we make this 1 to 2? By multiplying 2. So R3 will be R3 minus 2 of R1. Devi, is it clear to you, or I will explain again? Yeah, for any matrix you need to make this thing 0. If in some example, if you don't get 1 in anything, first divide it and make it 1. Okay, then plus minus. So after this process, A will be 1, 1, 2, 0 minus 2 minus 1, 0, 2, 1, 1, 1 minus 1. It has become 0. Now we want this 0. What we have to done? Just plus minus 2. 2 plus minus 2 will become 0. So new R3 will be R3 there is some problem. Okay, R3 plus R2. So A will be 1, 1, 2, 0 minus 2 minus 1, 0, 0, 0, 0, 0, 0. Okay, so only 2 row exists. The rank of A will be 2, and from here if we omit this part, it is matrix M. For matrix M also this row is already 0. So rank of M is also 2. Devi, do you have any problem, or is it clear? Or I can like give you another example. I think problem number 9 is also some kind of this.
Excuse me, ma'am. Ma'am, is it necessary to reduce this 1 from second row, like to 0 in the first place, and then 2 from third row? Third row, second column. It's like necessary to reduce these 2 components only.
Like you need to reduce this component and this component. Okay, what is the rank of a matrix? The rank of, like after this is the like lowest you can go. The subset of this matrix cannot be reduced. This is the meaning of rank of any matrix. You can get to this point anyhow, but it is easy. It is a formula, like you make it this to 0, then at the same point try to make this 0. Then if it is possible to make all those 0, then you can say it is 2. But after doing this, if this row doesn't make all those 0, then you can say that rank is not 2, it is 3 higher. It is like formula that you target those components. You don't need to worry about like 12 components at once. You just make those points target. Can we make this? If we do that, it is a step. If we do this step and this step, is it coming like that? If it's not, then rank is higher. If it is, then rank is that thing, like this. If you like, if you don't have any like step by step process, and you are like focusing on all other like components, then it will be very cumbersome for you. That's it, nothing else.
Thank you, ma'am. It is much clear now.
Okay, because it is like step by step, nothing else. In problem number 9, let me explain problem number 9. Like, it is a greater matrix, like 4 by 4 matrix. First, we need to focus on 3, 1, 5. To make 3 to 0, we need to minus 3, minus to make 1 0 minus 1, make 0 5. Okay. So first set of our task is R2. New R2 will be R2 minus 3 of R1. R3 will be R3 minus R1. For any step, like for first step in this like equation also, for first step I have kept R1 fixed. For next step, R1 and R2 both are fixed. I have added R2 to R3. Okay, because we can see here like R3 is negative of R2. For any step, keep one row fixed. For first step, keep row 1 fixed, just for simplicity. R4 will be R4 minus 5 of R1. So then what will it will be 1 2 2 4. 0 minus 5 minus 2 minus 7. Let me check if the recording is still on or not. 0 minus 5 minus 2 minus 7. 0 minus 10 minus 4 minus 14. Now here you can see that this row or this row is same, and this row is double of that. Now simple, if you minus R2 from R3 and minus 2 of R2 from R4, both of this row will vanish at once, right? So only 2 row will sustain our grilling. So the rank of a matrix is 2. Okay.
Ma'am, rank of M is also with 2.
In which question? Question number 5.
ম্যাম আমার একটা প্রশ্ন ছিল যে র্যাঙ্ক এ মানে এ র্যাঙ্ক 2 আবার এম এরও র্যাঙ্ক 2, এটা হচ্ছে ম্যাম ওই স্লাইডটাতে যান যে কোনো একটাতে।
Yeah, here. Yes.
হ্যাঁ ম্যাম।
Rank of M is 2 and rank of A is 2. I have proved that rank of A is 2. You can also prove that rank of M is 2. This process is again the same, because here M is what? M is like, it is a M, right?
Yes.
The same process will follow and it will give you that. So that's why I can say that rank of M is equal to rank of A. But by chance in any question it appeared like that, what was that? Yeah, it was one. It was 1 1 minus 0.
ফোর্থ কলামে যদি একটা রো ভ্যানিশ না হয়, মানে নিচের রোটাতে যদি কোনো কিছু থেকে থাকে জিরো বাদে, তাহলে কি তখন বলতে পারি যে এ এর র্যাঙ্ক 3 আর এম এর র্যাঙ্ক 2?
Yes, if in any like question it appears that 1 2 1 0 minus 2 minus 1 1 and this is 0 0 0, here a component exists 5, then rank of A will be 3, but M is like this portion na. For M, last column has vanished, so rank of M will be 2. Okay?
Okay, ma'am.
Yes, we can do another example. Another example of what? Row reduction. Currently I don't have another example of row reduction, but I promise in the next class I will do several problem of row reduction for you. Okay, I have come with from mathematical methods books, basic mathematical methods books, and I will like explain to you. Is it okay, Devi? Because I don't have like, okay. It is normal, because row reduction at your age it was very difficult for me also, so just follow the steps. Equation 5 has been done. Okay, like we have done in question number 9, quickly finish question number 10. Okay, if V1 be the space consisting of 2 by 2 matrices with complex entries and complex number forming the scalar field, and V2 be the space consisting of 2 by 2 matrices with complex entries and real number forming the scalar field. So don't mix here in this question, don't mix V1 and V2. You need to see if V1 forming vector space, and separately you need to see if V2 making vector space, right? See those things and then choose options. For V1, first we try to prove if V1 is a vector space or not. Okay, so 2 by 2 matrices, V1 is 2 by 2 matrices and its entries are complex. Okay, so A is a matrix. Okay, B is also matrix. A belongs to V1, B belongs to V1. Okay, so all of the entries, or you can say entries or components of the matrix 2 by 2 matrix is 4 component: A1, A12, A21, A22. These are all complex. Okay, and B is also like that: A1, B12, B21, B22. Okay, so again see, we are doing this. I have already mentioned that instead of doing A plus B belongs to vector space and alpha A also belongs to vector space, we do it at a one go. Alpha A plus beta B. Okay, matrix can be written as also like that, like this matrix can be written like Aij, or it is like small a, and this matrix can be written like Bij, right? So alpha Aij plus, the components are written like this Aij, but the matrix can be written like this, and beta Bij. Okay, and the C, if we are writing A and B like this, C has to be written by this. Okay, so what does it mean? This line means, if let us put I is equal to 1, j is equal to 1, right? We have four options: C11, C12, C21, C22, because as it is 2 by 2 matrices. Okay, so let's put C11. What we will find? Alpha C11, which is small c11. What will it will be? Alpha A11 plus beta B11. If alpha A11, which is small a11, here I have made a mistake, it will be like this, beta A11. We have already said that A belongs to V1. That means that every like entity in V1 is complex entity. So A11 is complex, B11 is also complex, and alpha and beta we have assumed that belongs to C. C is a vector space. Also, they also made scalar field. So this thing, alpha A11 plus beta B11, even if alpha beta is normal real scalar, when real scalar is multiplied by a complex number, it becomes complex number. So C11 is complex number. Similarly, C12, alpha A12 plus beta B12, C21, alpha A21 plus beta B21, all C22, alpha A22 plus beta B22, they all are complex numbers. So they satisfy closure rule. Then we need to satisfy identity rule. Identity is 0. In most of the cases, identity is 0 matrix or 0 function or 0 vector. Okay, for 0, for a matrix A, we like have to add something 0 which can give us back A under addition. If you know the concept of group for under the rule of addition, the condition for vectors, linear vector space, is also that thing. So we need to add something with A that can give us back A. So all the entry has to be 0. 0 can it can enter any group, scalar, any group in scalar field also. Here we have mentioned that is scalar field. So it is real number, you can say 0, like the complex number is written by this 0 plus I0, it is also a complex number. So 0 belongs to V1. Then identity is proof inverse. So for A, its inverse will be A dash, which will give us 0. So for every component of A dash need to be minus A11, minus A12, minus A21, minus A22, right? So A dash we can write A dash ij like minus A ij, right? Because it is what? Minus of this. Aij belongs to V1 minus Aij also belongs to V1. So it follows the closure property. Closure property as well as identity, and also has inverse. Similarly, you can see that V2 is also a vector space. The V2 be the space consisting 2 by 2 matrices with complex entries and real numbers. Here we have assumed that A11 is a complex number, but there it will be said that A11 is real numbers. Like, so everything will be the same. A11 is real, A12 is real, A21 is real, A22 is real, same as B11, B12, B21, B22. So that will make C11, C12, C21, C22 all real. And there we will assume that alpha and beta is a real and real numbers, because the main thing, the matrices are in themselves are real, so we don't need that alpha scalar as a complex number. So V1 and V2 both are vector space. Now let's go to 4. Let A be the set of M n matrices with real elements and B be the set of M into n matrices with complex elements. We wish to think of the elements of these sets as vectors. Okay. So let us take the operation of addition of matrices like we are familiar to the addition of vectors. Also let us restrict scalars with which we multiply the vectors to be the real number. Which of the following statement is true? It is similar to question number 10. Only difference is that those entries here, element of these sets, are vector A11, A12, A21. Like, it is not like limited to like 4 elements. M into n elements is there. Okay. So there we have assumed that A11, A12 either complex or real, but both times they were scalar field. But here they are vectors. In the similar process, everything will be the similar. When A11 and B11 both are vectors and they are multiplied by like scalars, C is equal to alpha A, not this, alpha A plus beta B. All the elements alpha and beta are real number. Okay, they are scalars. Alpha and beta are scalars that can be real or complex. Okay. Then when scalar multiplies vector, we know that it is scaling the vector, the magnitude of the vector, or or sometimes it reverses them. So every component of A and B, if is vector and it is multiplied by a scalar, it will still a vector, and when we add them, C will be, every component of C will be the vector. So the similar 10, we can say both of A and B are vector spaces. Is it clear to you, or anyone have any problem?
Yes, ma'am. Yes.
It's clear? Okay. 5 I have already explained. 6. Which of the following statements is true? Our set of mutually orthogonal vectors may or may not be linearly independent, and the linearly independent set of vectors need not to be mutually orthogonal. So let us see what is true. Okay, let us assume two vectors, alpha 1 and for simplicity we can take a1 and a2. We are using k vector notation here. A is dual vector space consist of k vectors and bra vector, or is it bra vector just like linear vector spaces are denoted by k vectors? Okay, if linear vector spaces are denoted by k vectors, its dual vector space need to be denoted by bra vectors only. Okay, dual means it's normal vector spaces complex conjugate all the time, like alpha is complex conjugate will be like this. Okay, independent condition 0 when alpha 1 is equal to alpha 2 is equal to 0. Okay, and if two vectors are orthogonal, it is the condition of linear independent. Okay, the condition of orthogonality is this: a1 a2 need to be 0. Okay, so it can be written by generalized ai aj need to be 0, but it is not always 0. a1 has to be 1. So we can write this way: when I not equal to j, it is 0, but when I is equal to j, it is 1. Okay,
Kronecker delta I.
Hello.
Yes, ma'am. Kronecker delta I.
Yeah.
We can.
Yeah, delta ij, you can say that. You are saying this, na?
Yes, ma'am.
Yeah, or you can write this like way. Yeah, and now we will consider a1 a2 like up to a to the power n. They are consisting of if they are linearly independent or not. For this need to be linearly independent. See, to follow this, to satisfy this, we don't need any orthogonality. Okay, linear independence when alpha 1 is equal to alpha 2 is equal to 0, it is okay, 0. Even when in here also if it is 0, when all the coefficients are not 0, it is good to go. We don't need like for linear independency, a1 need not to be 0, a1 a3 need not to be 0. For linear independency, we don't need each one to be orthogonal to another. But for orthogonality, let's multiply with a bra vector am. It has to be 0. It is also has to be 0. It is also has to be 0. But here we can see this portion is already 0. Now we multiply am 0, it will give us 0. So this is the condition of linear independency. It is the condition of mutual orthogonality. So to follow all these things 0, 0, 0 for all the inner products 0, linear independent condition has to be satisfied. So the answer is a linearly independent set of vectors need not to be mutually orthogonal, but a mutually orthogonal vectors need to be linearly independent always. Okay. Now question number 7. Suppose we consider the space of two-dimensional vectors in which both components are real. Can we define the inner products of two vectors ax ay and bx by as a dot b ax bx plus half of ay by? Would this be a legitimate scalar product? If yes, how does the Cauchy-Schwarz inequality play out here? We know a dot b is equal to have to be b dot a. So a dot b is equal to given by ax bx plus half of ay by. So b dot a have to be bx ax plus half of by ay. Let us assume C, a vector which is Cx and Cy, and multiply that with alpha A plus beta B. Okay, Cx is equal to alpha Ax plus beta Bx, Cy into half of A alpha A y plus beta by. What will it become? Alpha into Cx Ax plus half of Cy Ay to beta Cx Bx plus half of Cy By. If A dot B is like this, Ax Bx, so it will be alpha into C dot A plus beta into C dot B. Now we have proved that linearity. We know that it should like this, and we have find that it is like this. Now positivity is what? A dot 8, self product. So when A dot B was there, it is AX BX plus half of AY BY. Here it is need to be AX into AX plus half of AY into AY. We know that A dot A greater than or equal to 0. When it will be 0? When A is 0, then only square is equal to 0. Otherwise it is not a null vector. So that given definition, which is this, has satisfied all the required properties. So it is a legitimate scalar product. Okay. Now we need to prove Cauchy-Schwarz inequality. So what is Cauchy-Schwarz inequality? Cauchy-Schwarz inequality says A dot A into B dot B needs to be greater than A dot B whole square, or you can say A dot B A dot B. Okay, so put the values there. Here what will be that? AX BX plus half of AY BY whole square. It will be AX square BX square plus half of AX square BY square plus half of AY square BX square plus half of AY square BY square needs to be greater than AX square BX square plus 1 by 4 of AY square BY square, it is also 1 by 4, plus 2 into AX BX half of AY BY. This portion cancel out this portion cancel out this portion, and you can see half of AX square BY square plus AY square BX square greater than equal to AX BY, okay, AX BX AY BY. So it is like can be written as BX B square BY square plus AY square BX square minus 2 of AX BX AY BY greater than equal to 0. It is also can be written as AX BY minus AY BX whole square greater than equal to 0, which is a true thing. Any square has to be greater than equal to 0. It is true, that means this thing is true. So it satisfies Cauchy-Schwarz inequality. Only one problem is left, which is which of the following statement is true. If two vectors are multiplies of each other, the Cauchy-Schwarz inequality for them becomes an equality. The Cauchy-Schwarz inequality becomes the equality only for two vectors that are multiplies of each other. For certain choices of the inner product, it may be impossible to find vectors for which the Cauchy-Schwarz inequality is an equality. And consider the vector space of complex number for which the scalar product is defined as Z1, Z2. Here the Cauchy-Schwarz inequality is always an equality since the two such vectors are multiplies of each other. So here A, B and D is true. if z1 is a vector which are multiplies of each other, z1 and z2, they are multiplies of each other, so z1 will be the alpha into z2 multiplies, and similarly the two vectors are multiplies of each other, its complex conjugate will be z1 alpha dash z2. Now for Cauchy-Schwarz inequality, we have to prove that alpha star can be written as like this also. So alpha alpha will cancel out, then z1 z1 z2 z2. So the Cauchy-Schwarz inequality becomes an inequality if and only if the two vectors are multiplies of each other. So B is true, A is true. And if we consider the vector space of a complex number for which the scalar product is defined is that, we know the scalar product is always defined as that Cauchy-Schwarz inequality is always an equality since any two vectors are multiplies of each other. So we have proved that if one vector is multiply of other, also we can write this, if z1 is equal to multiply of z2, z2 is also multiply of z1. We have done that. Z2 has been written like this, 1 by alpha z1. So it becomes equality since when the two vectors are multiplied of each other. Okay, so question number A, B and D are true. So all the questions are solved, and I will upload this thing in the drive. You will get those solution, and next day I will do more row reduction problem, Devi. Don't worry. Anyone have any problem? Okay, I suppose Devi and Payal, you two are the remaining on. Most of the people have left. So if you don't have any problem, I will discuss next week the week 2 problems, and first I will discuss row reduction problems. Okay, so
Okay, ma'am. Thank you.
okay, thank you. I'll end this meeting. Thanks.